The baker's secret. Why perfection is a myth. Imagine asking a baker for a loaf exactly 10 inches long. The baker would smile, knowing true perfection is impossible. Dough rises unpredictably, ovens fluctuate, and the final loaf might be 10.1 or 9.9 inches. In reality, we accept a range, say 9.8 to 10.2 inches. That's tolerance. Tolerance is a practical agreement about what's good enough. It lets millions of imperfect parts work together seamlessly. That's the real secret behind every well-made thing. The rules of imperfection. Types of tolerances. Once we accept every dimension needs a tolerance, we must decide how to specify it. The simplest way is, just state the maximum and minimum sizes, like 9.8 and 10.2 inches, or use 20 mm plus 0.1 mm means the part can be 19.9 to 20.1 mm. This works when deviations in either direction are equally acceptable. Sometimes, only one direction matters. That's 15 mm, 0.2 means the part can be smaller but never bigger. There's also 15 mm, 0.2 millimeters for when the range isn't centered. Each method is a way of saying, perfection isn't required, but here's how close you need to get. The choice depends on function and manufacturing process. These conventions keep everyone, designer, maker, inspector, on the same page. Tolerances are the language of practical engineering. They define the boundaries of what works, and they make mass production possible. The perfect fit, clearance, interference, and transition. Tolerances aren't just about single parts. They control how parts fit together. A always leaves a gap, so parts move freely, like a wheel on an axle. For example, a hole 25.0 25.1 mm and a pin 24.8 24.9 mm always guarantees a gap. An is the opposite. The shaft is always bigger than the hole, so you must force them together. Think press-fit gears. Example hole 49.9 to 50.0 mm, shaft 50.1, 50.2 mm. Always a tight squeeze. Is in between. Sometimes a gap, sometimes a tight fit, depending on the actual sizes. Example, hole 30, 30.02 mm, shaft 29.99, 30.01 mm, could be a slight clearance or interference. The right fit depends on whether you want movement, a tight hold, or something in between. Understanding fits is key to making assemblies work. It's how we ensure parts come together as intended. Stacking the blocks, the peril of tolerance stack-up. When assembling multiple parts, their tolerances add up, sometimes with big consequences. Imagine 3 blocks, each 50 mm plus 0.1 mm. Each could be 49.9 to 50.1 mm. If all are at their max, the assembly is 150.3 mm, 0.3 mm over nominal. If all are at their min, it's 149.7 mm, 0.3 mm under. The total assembly tolerance is now 0.6 mm, not 0.2 mm. This is called small variations multiply. If your assembly needs to be tighter, you must tighten individual tolerances, which raises costs. Stack-up forces engineers to think about the whole system, not just single parts. Managing it is crucial for reliable, cost-effective design. Section 5. A new language. An introduction to GD&T. Simple tolerances control size, but what about shape, orientation, or position? That's where GD&T, geometric dimensioning and tolerancing comes in. GD&T uses symbols to define how flat, round, or aligned a feature must be. For example, a flatness symbol with 0.05 mm means the surface must lie between two planes 0.05 mm apart. No waviness allowed. GD&T can also control the position of holes, not just their size. Is a powerful GD&T concept. If a hole is made larger than the minimum, you get extra positional tolerance. For instance, a hole allowed from 10.0 to 10.4 mm. If it's 10.3 mm, you get 0.3 mm extra for its position. This flexibility rewards good manufacturing and reduces cost. GD&T links size and location, making tolerances smarter and more functional. It's the universal language for precision in engineering. Section 6. The art of good enough. Choosing the right tolerances. Picking tolerances is a balancing act between function and cost. Tighter tolerances mean higher costs and more rejected parts. The rule: specify the loosest tolerance that still works. Know your manufacturing process. Don't demand more precision than it can deliver. For example, don't ask for plus 0.01 mm on a rough wood part. Focus tight tolerances on critical features, like bearing bores. Non-critical features can be much looser. Use industry standards and tables. They're based on decades of experience. Standards save time, reduce risk, and ensure compatibility. Don't reinvent the wheel for every part. Smart tolerance choices make products reliable and affordable. That's the art of good enough engineering. Section 7. The moment of truth. Inspection and measurement. Designing tolerances is only half the job. The other half is checking if parts meet them. This is inspection, or metrology. For loose tolerances, simple tools like calipers or micrometers work well. Calipers measure to about plus 0.02 mm. Micrometers go even finer. For complex or tight tolerances, advanced tools like coordinate measuring machines, CMMs, are used. CMMs use probes and software to check shapes, positions, and profiles with high accuracy. Gauges, like go, no-go, give a quick pass-fail for features like holes. The right tool depends on the tolerance and feature. Inspection turns design intent into real-world quality. It's the final check before a part goes out the door. Section 8. Common stumbles and simple fixes. Even experts make mistakes with tolerances. Over-tolerancing, making everything too tight, wastes money. The fix: review each dimension and loosen where possible. Ignoring stack-up can ruin assemblies. Always analyze cumulative tolerances before making parts. Specifying impossible tolerances for a process leads to failure. Consult with manufacturing early. Ambiguous drawings cause confusion. Use clear, standardized practices and GD&T symbols. Talk to the people making the parts. They know what's realistic. Use standards to avoid misinterpretation. Clear communication and smart choices prevent costly errors. Tolerances are powerful. Use them wisely. That's how you turn good designs into great products.